Okay, so for our final project, we decided to do like a n-body gravity simulation using the OpenGL package. We essentially have this gravitational body class that simulates like one planet. It uses this math vector struct to like handle all of the position vectors and the velocity vectors. Each gravitational body has a density, a mass, a color, a velocity, and a position. Um, and I mean, essentially, each body on its own doesn't do very much, but when you use this gravitational system class, which Ethan will talk about, does a bit.
Yeah, so the gravitational system class essentially has a collection of gravitational bodies and then simulates gravitational interactions between the bodies in the vector and does all the calculations for that. So there are a bunch of helper methods that essentially contribute to one kind of overall method, which is update all, which essentially takes one time step and runs the simulations for that, and that will update acceleration, velocity, and position vectors for each object in the collection of, or in the vector, which is each one of those objects being a gravitational body, and then it also deals with calculations for when the different gravitational bodies collide, which I think we'll talk about a bit more later.
Yeah, and then our main function actually draws everything to the screen and updates everything, but it'd be probably a little bit easier to show you than talk about it for that. So if I just run it, initially you see it'll initialize with 500 random bodies. They all have a random initial velocity, a random mass, and a random color. You can see as the bodies collide with each other, there's some collision detection that does a little bit of stuff. Ethan, did you want to talk about that?
Yeah, so when two bodies collide, we actually do the collision based on the drawn object. And essentially, when they collide, the masses get combined to kind of like reform into the new body, the the combined mass. And then the color is like the combined body's color is the average of the two bodies that collided. And then where we model each of the collisions as like a completely inelastic collision, um, effectively meaning that kinetic energy is not conserved, but momentum is. I think that's about it. Oh, the density is also averaged out.
Yeah. There's a few like key input commands. Like if you click anywhere on the screen, it'll add a new body to the simulation. You can change the mass of that new body by like hitting different key commands. Like if you hit 6, it'll make a slightly bigger planet. If you hit 9, that's the largest planet it'll add. You can see it starts to get pretty big. If you hit P, it'll pause the simulation. So if you want to go around and like insert a few bodies in places that you want, then you can hit P again, and it'll play the simulation. And then the last one is if you hit R, it'll just reset the simulation or clear the screen. So like if you want to clear the screen and just make your own setup, you can kind of just go around here and then add a few bodies and then unpause it, and you'll see how those bodies will interact with each other. Um, I think for my computer, it can kind of comfortably simulate around 500 bodies before it starts to get a little bit sluggish. There's definitely a few like optimization techniques that I would have liked to implement if we had more time, but I couldn't really wrap my head around them, to be honest. So we didn't really get to those. Do you have anything else to add, Ethan?
Yeah, no, I mean, I thought this was a really fun project to do. At first, when we were first talking about doing it, I was like, "Oh, this is going to be like really overwhelming," and then we kind of broke it down, and suddenly it was like, not particularly easy, but certainly doable. And so it was really satisfying to see it come together, and I think the result is pretty fun, pretty interesting.
Yeah, I agree. All right, that's our final project.